this computer. Okay, today Daniel Haenelt is here. Thanks for everybody who could join, even though there's this eye tracking workshop in parallel. And as I said, this is going to be recorded, and people from the eye tracking workshop can also watch it later online. So Daniel Haenelt, I think, is known by most of us. You were visiting NIH, I think, April last year, a bit more than 1.5 years ago. Maybe Daniel is known in my circles for his work on ocular dominance columns during his PhD in Leipzig, specifically looking at spin echo and gradient echo and vaso, and also doing decoding, and then looking at the thick and thin stripes in V2 with structure and function. Today, Daniel is presenting a study that he's ramping up, a study that he appreciates feedback because it's something he wants to start doing, and I'm looking for the title. The title is Understanding the Biases in Functional Magnetic Resonance Imaging, and you saw the abstract. And maybe you can start sharing your screen.
Yeah, okay. Okay. Do you see the? Does it look good?
Yes, we see the kiosk view, so it looks good. Yes.
Okay. So then I will just start with the presentation. Okay. Okay. Yeah. First of all, thank you for letting me present my work in the group meeting. So I think understanding biases and fMRI is quite a bold title. So it's just a yeah, kind of a overarching title. My projects might fit in, but I will only present some. No definite results today. But yeah, overall, yeah. So we know that fMRI is an indirect measure of brain activation, and it depends on the hemodynamic response following neuroactivation, and also regarding high resolution fMRI, where we might be interested in cortical layers and cortical columns. We know that draining veins are the main limit in spatial specificity regarding bold acquisitions. And so this might be the biggest bias in bold fMRI. But there also so the fMRI signal also depends on a multitude of other influences. For example, there's also the known effect on cortical folding with respect to the static magnetic field, which influence the bold signal. But there might also be partial volume effects. For example, fluctuations due to pulsatility effects, the gray-matter CSF border can influence the fMRI time series, but also processing steps. For example, sampling the time series data to a cortical mesh can have a big impact on the analysis, which was recently discussed by Jagannathan and co-authors, who showed that, for example, in function connectivity analysis, the heterogeneous mesh density, which because the mesh is much more dense in the cycle depths than in the top of the gyri, influences, for example, connectivity analysis. And in our project, we want to understand these relationships between fMRI and different biases, which can influence the fMRI time series. And this was a project which was started by Olivier Wiesmann, who was a postdoc in Jonathan Polymeni's lab, and I when I start in his lab, I continued working on this project, and so the idea is that if we have an fMRI time series and there are potential biases, these are probably complex and nonlinear, but if there's a kind of a relationships, can we use a deep learning model to learn this? And if we can learn such a relationship, so we would like, in the end, understand it better and maybe also be able to remove those biases. And in the end, so what we are doing then in practical terms, so we use a unit architecture, which is a fully convolutional neural network, and we try to predict a multitude of anatomical metrics, for example, cortical thickness from fMRI time series data. And then as an input, we don't use the full time series, but kind of a summary measure. And so we always use the coefficient of variation from fMRI time series data. And for this project, we used an open data set, namely the natural scenes data set, which was recently published. So the data sets consist of 8 participants who were scanned multiple times, many times over 1 year. So we have for each subject many time series resting state acquisitions, which we use then to train this model. And they also acquired various anatomical data from which we estimated then cortical thickness and other metrics. So the input data for those models are always kind of 2D images sampled on a rectangular grid. So to achieve that, we used a resting state time series, applied a temporal bandpass filter, computed the coefficient of variation, and after applying a spatial bias field correction and sampling on the cortical surface mesh, we used the surfer package to map the data sampled on the cortical mesh to a rectangular grid. And since we mapped the whole surface from one hemisphere, we also have these non-cortical regions from the midline, which we had take care of during model training and inference. And so we have those data for all 8 subjects, and we trained our unit using our leave one subject out cross-validation scheme, and in our loss function we acknowledge the non-cortical areas by also not considering then to in computation of the loss, and we use some data augmentation techniques also, mainly to be more independent of these non-cortical regions, so that the network doesn't learn where these mask regions are, and so we always use some flipping of the images and translation to move these mask regions around the image. And yeah, this shows some exemplary results where we predicted, for example, cortical thickness from fMRI data. And so this shows is the original map from one subject, and this is the predicted map from the network. And overall across folds or across subjects, we could achieve a square measure of about 0.3, which and we got similar results if we instead of predicting cortical thickness when we predicted mean cortical curvature, which we ended also in a square of 0.3. And So we know that these are related and they share some similarities, and so we also know that for example, cortical thickness and can also be is related to cycle depth. So we also want to look how this relates to cycle depth measure, and we predict cycle depth instead of curvature and cortical thickness. We get a much higher prediction accuracy. So this yeah gives my so that it might be that kind of the underlying reason why we can predict cortical thickness and cortical curvature is that we that cycle depth information is mainly preserved in the fMRI data, and so that there might be different reasons why we have cycle depth information in fMRI data. For example, it could be driven by as I stated before, by the heterogeneous mesh density, because we have denser meshes and deeper in the cycles. But if we use surface area and try to predict this information, so the model fails in predicting surface area, and the same is also for partial volume estimates. So it also cannot learn this metric. So this is kind of an open question for, at least for me, what how can we interpret these results? But yeah, these are still results I just got recently, and I have to do some controls, so that I'm sure that the network really learns valuable information and not only the mean cycle depth topography across subjects, because we know this cortical folding patterns also share have some similarity across subjects. So I will also, which I didn't have time now, but I will also include some control analysis where, for example, have an input just a flat mat, or input the non-cortical areas to see if this is not driving the inference, or and then so as I shortly also discussed, so one of the open questions is what's the driver of the abilities to predict cycle depth from fMRI data. Maybe is this just distance to the receive coil elements, but we also use the bias feed, spatial bias feed correction of the input data, or is this maybe the heterogeneity of the venous vasculature with bigger veins and the fundus of the sulci, or something else. So this will be the next step in this project. So maybe I will use also spatial filtering, maybe to to investigate different noise regimes, and see if from this experiments I can make better interpret these results. And I will also try to create these so-called salience maps, which were also used by this publication by Markus Frey, which is this deep MRI paper, which is probably now also discussed in the eye tracking workshop. I don't know, but they in their network, I found it quite clever. They use the shuffling procedure where they always kept maybe 10% of voxels or pixels at the same location, but shuffled everything else around and did it then a couple of thousand times to see which pixels or voxels were driving the network most, and so to investigate, well, what's the driving, which are the driving voxels, which have the most information for the network. And their publication, they could show, for example, it was where the voxels where the eye were located. And so and this might give us some insights why from which parts of the map the most cycle depth information is taken from. Yeah, but I'm also interested in draining veins and removing maybe draining veins from fMRI data. So this project is more about understanding or trying to understand a little bit the bias, maybe also to remove some of the biases in future work. So in the second project, which is kind of a continuation of the project.
Could I ask about the first project, if I understood this correctly? So you're using the volumetric data, right? And you have like a quote unquote only the standard deviation over the mean, like kind of the TSNR as an input in 3D space that you give to the model. Is that right?
No, it's the data is sampled on the surface, and then on the mid-cortical surface. And this data is used. And this data is mapped then to a kind of a rectangular grid.
Gotcha.
And this is
okay. And then the input data are kind of the standard deviation, mean divided by standard deviation in that flattened grid.
Yeah.
So you might, maybe you list this in controls, but this might also mean that you're basically quote unquote just looking at the same segmentation errors that FreeSurfer might have in kind of as a function of sulcal depth that usually cuts off the bottommost part of gray matter, the bottom of a sulcus, and then cuts the superficial layers at grounds of a gyrise. So you're not looking at 3D data, but you're looking at the spatial structure. Is that right? So, so it's kind of not looking at individual vertices only, but basically based on the local geometry of that vertex, it decides whether or not there is like which cortical thickness it is or which sulcal depth it is.
Yeah. It might. Interesting. It might be also just related to limitations of in segmentation and but I think it's one of the next steps would be to investigate it further to find out. But if it's just kind of, or if it's just driven by these by segmentation errors, I would be still surprised that it can then from this information predict cortical thickness so well. And I think that might be something more.
So you're saying that partial voluming is not a good predictor, right? Because that could explain it. If, for example, the mid-gray matter is kind of effectively touching white matter, then the standard deviation, like the TSNR, would effectively be different. And if you have a thinner cortex, then this bias would be stronger. But if you see that partial voluming is not a kind of a good predictor, then probably that's a good control already. Cool, thanks.
And for the second project, so we haven't acquired much data so far. So just mainly an outline of the project. And so we know that for generation tasks, so diffusion models are very, very good and very popular. So we thought that we can use kind of a diffusion model, which here I present as a dual diffusion model to remove macrovascular biases from bold fMRI data in formulating an image translation task where we want to kind of translate our microvascular weighted spin echo EPTI data to a gradient echo bold data using such a network. And so we want to use EPTI because it has several advantages. So we expect that it has it has a more pure T2 weighting than if we use spin echo bold with alone readout train, and we it also produce a lot of images for during the echo train, and so our idea is then to further conditioning this diffusion process using this echoes, but we also want to further physically constrain the model by estimating extravascular field contributions from the mesoscopic or from the macrovasculature to further constrain such a model. So it's just kind of I don't want to get much into detail, but because I'm still just started with the project, but the main idea is then to also acquire next to spin echo and gradient echo bold data, also some anatomical metrics for high resolution time of flight and QSM data, from which we would then try to estimate, or from QSM we would then compute venous oxygen saturation, and from the time of flight we would then segment mesoscopic arteries and veins. And from this data, then we would try to estimate these extravascular field contributions, which then we would also use in our model to further constrain the output or the translation. And so one of the first problems we face is to acquire these data, because if you want to go these high resolutions, like for example 350 microns, which data kind of subject motion gets really a limitation, and so if we so this is kind of as an example which we acquired. So we acquired here a theta weighted flash, which from a coronal oblique slab, which where the acquisition time was around 50 minutes. And so if we, of course, during the 50 minutes, we participants move a little bit, and so this will result in artifacts in image. So in this case, the subject movement was that large that the data were almost not usable anymore. So to improve image quality, and so we wanted to start using these volumetric navigators technique for prospective motion correction. So we did in a collaboration with Robert Frost, who implemented these in the grand echo sequence then, which we use then. And so the basic idea of volumetric navigators is that you stop after, for example, 100 the acquisition of each few seconds, and then acquire a very fast low resolution EPI scan, which is then be used for prospective motion correction before you start acquiring the next bunch of case-based lines. And so this is normally the advantage is that you can do that without changing the magnetization, but the problem is for these high resolution scans we wanted to acquire is that we can only acquire a slab of a few centimeters, where it then gets tricky. So because if we use the same slab for the navigators. So we this probably won't be enough to have good registrations. But if you have a slab selector flash scan, but with a whole brain navigator, so we end having these shadows shadow effects. So where our SLAC selector flash scan is located. So and then this we wanted to test it anyway, and so we asked ourselves, is this a limiting factor for these for prospective motion correction? And it turned out we think it still works quite robust. And so, for example, so that's now a beta participant. So acquisition was also around 50 minutes. But we used the navigators in the scan, but prospective motion correction was turned off. And so I show here in kind of an Excel slice with the minimum intensity projection across some Excel slices, which shows nicely here the some veins in these theta star weighted data. And so if we turn on prospective motion correction, we see an improvement in image quality. And so this encourages us to use this technique now for the acquisition of our time of flight and QSM data. And so as next steps, so Robert Frost is also mainly working on implementing new features to the sequence. So his main ideas is now to add also dual echo API, which can then be used for prospective motion correction and also for visual estimation for online shim correction. And we also plan to acquire high resolution time of flight data with volumetric navigators in the near future. Yeah, thank you for your attention.
Thanks a lot. I really like the navigator approach. So this,
yeah, it really worked well. Yeah.
And maybe you mentioned it, but like this was a slab selective approach. So basically, like it was done in real time, right? You didn't have the navigators and then use the navigators in the reconstruction later to account for it, but you literally kind of recalibrated or changed the gradients form for the next excitation pulse.
Yeah, exactly. Yeah. So I think the at the time was around for this 350 micron protocol 1.5 minutes. So every 3 seconds we acquired a navigator which took 200 milliseconds, and we added 200 milliseconds of that time for the feedback loop for prospective motion correction, and also to mitigate eddy current effects.
Gotcha. And you're not worried about kind of T1 steady state history effects, that you have a steady state with Ernst angle, and then you have a break, and the navigators kind of break that steady state, and then you're going into it? Or is the 3 seconds your volume? No.
Yeah. So there will be some changes. So we did some tests where we yeah, but it's also preliminary. But we also acquired some data to explore the changes and to examine the changes in contrast with and without navigators, and we didn't find any big changes.
So ultimately, to use the navigators, you're using kind of a volumetric alignment, get those coordinates, and then put them back into the sequence. For that, like depending on how you estimate the volumetric alignment, it would be straightforward to kind of use a mask to estimate this alignment that kind of cuts out this slab artifact to begin with, right? So, or like, for example, when I think about retrospective motion correction in SPM or ANTS or whatever, or AFNI, I can always use a mask where I'm optimizing my motion estimation too. And maybe this is not something you can do to, like, with respect to the real-time estimation of the motion parameters, but it should not be kind of impossible to kind of get rid of this little slab artifact in your navigator images to just cut them out from the motion estimation. Or maybe you're doing that already. I'm not sure. I understand the problem that you mentioned with that one, right? You have this black bar, but you still have enough structural signal everywhere else. So if you just exclude that part of the brain from your motion estimation to get the coordinates of the kind of displacement, then you would definitely not be sensitive to that. Like, for example, in 3D I'm struggling a lot with these kind of transition areas of my slab, which has a finite kind of sharpness, that very often the motion estimation kind of tries to align the borders of the slab. And for me, this is actually a real limit, that kind of motion in that dimension, in that direction, is usually not accounted for. However, if you basically trunk out those masks or don't use them for the estimation of the mutual information or cross correlation, whatever metric you use for the similarity with the alignment, then I like solve that problem. So I'm wondering if maybe this might be a viable strategy for you too, that you're just only estimating the displacement outside the borders of that little slab.
Yeah.
But you're saying that it doesn't really matter so much in this case anyway. Well, I
Yeah,
guess
we still also, so yeah, Robert mostly works on this adding new features, and yeah, I can I will discuss it with him. I don't know if he already thought about masking out this the slab region. So I don't know if a mask is used for this registration, to be honest, but he also for the for the B-naught estimation, so he always applies a mask for to update the shim. But yeah, yeah, we might try it out. Yeah.
Are there any other questions? Nobody's raising hand.
Well, it was great. Thank you very much, guys, for making this through.
There's no question.
I have a.
Yes.
Do you hear me?
Yes, we do.
This navigators, maybe it's more local question. Renzo may help me. Do we use in our CMS machines? How do you use it? I have no idea about this volumetric navigators. How do we implement this? Do we use it?
There are some sites and labs that use it for some studies. It's not very common. I think within fMRIF, people used prospective motion correction with the Connecticut system, which was not really reliable, and I think it hasn't been used for many years. I see that Jeff Dunn is in the call. They use it more regularly, also in application studies. Also, I think maybe for studies with Danny Reich, specifically for the same sequences, namely GRE, high resolution GRE and high resolution multi-echo GRE. I don't know the details of how they implement it though, and yeah, maybe Jeff can comment.
Yeah, we use retrospective motion correction, so we measure the movement and the B0 field changes, and then correct the data after the fact.
And one additional question: volumetric navigators are only required when you have no option of multi-echo recording like VASO. Is it correct, or like is it better? Like, I'm trying to understand if you have chance of having multi-echo, you can do motion correction that way?
We don't really use the EPI readout that VESO uses. So we do an interleaved 3D where we collect both in-plane and through-plane multiple shots. And then the navigator is also multiple shots. So we need, I don't know, maybe a second worth of data to get a full navigator signal. And that we use then for correction. So that's mostly correcting for slow variations. So respiration and slow movement in the scanner. So jittery movement wouldn't be corrected.
And Jeff, you're using this for SLAB protocols too, right? Not only like non-selective protocols. So the retrospective.
Yes, yeah, it's still SLAB, yes.
Okay. So you're not adjusting the gradients though. Yeah.
No, no.
Yeah. Cool. And this is similar resolutions, right? 0.35 or
Yeah,
something.
yeah. Similar resolution, great.
I mean, the reason I'm asking is like we have opioid use disorder subjects, and compared to control, chronic use of opioid is influencing their breathing patterns where respiration rate may not change a lot, but it gets shallow because the carbon dioxide detection and the hypoxia kind of issues are damaged by the opioid receptors kind of messed up in the brainstem. But
Oh, the oxygen sensors, you mean?
yeah, the chemosensors.
Right.
So I am looking at those data now, and I'm trying to get the best. And I don't know how vascular structure will be influencing this too. So I am really into like our Siemens machine will have an upgrade to XA30 system in 2 months or so, and I'm not sure we have time of flight sections already purchased too, but I'm trying to combine these vascular imaging with also motion correction with different types of people's respiration patterns. But maybe I am too far ahead of what we may need to do. I just want to hear what you may suggest.
Yeah, yeah. Yeah, we have primarily experience with fairly regular breathing. If they have any, you said that it's just shallow breathing, or that it's also irregular?
Oh yeah. There is some, yeah, it's more, I calculate coefficient of variation in the volume, respiration volume. It's different. Yes, also variation too.
Okay, yeah, yeah. Yeah, that's very tough. So that creates both strange field effects, right? Non-periodic field effects, but also non-periodic bolt fluctuations, right? Because
Right.
blood flow and blocks oxygenation will also change. So that
Absolutely. Right.
so both the fMRI and the anatomy will be challenging. Yeah,
Right.
we usually exclude those people. So we do overnight sleep studies with people that have any apnea or irregular breathing. We exclude them because that's too big of a challenge.
Right.
So I can't help you there.
Okay. We go with the simple solutions.
Yeah.
Address to be addressed later.
Yes, yes. So the multi-echo for the fMRI wouldn't work there either, right? Because now you get a bolt noise that that you can't really remove. It has the same echo time dependence as neural activity related bolt signals. So yeah, that's a big challenge.
Well, thanks for the input anyways. That's great too.
You're welcome.
So Daniel, for your second project, you want to basically get a more kind of holistic, multi-faceted view on kind of the microstructure to inform the fMRI time series. and you're thinking of the time of flight, and are you considering using like phase data too, specifically with the large draining veins, and kind of looking at kind of the blooming effect versus the draining effect of large draining veins at high resolution fMRI? That might add some value, right? Specifically for the modeling part.
You mean for the fMRI part?
Yes, yeah, like to inform the fMRI, yeah. Like you have all these auxiliary things, the diagrams, and yeah.
Yeah, this would be very interesting. Also, yeah, I think for the first try or first implementation of some toy model or so we don't plan to use phase data, but we already had discussions about maybe function QSM or how this can then maybe help the model. For example, so for these time of flight and QSM data, we only have kind of a baseline state. So would also be probably very informative to see these susceptibility changes driven by the stimulus, or yeah, definitely, yeah, but yeah, probably also very challenging.
All right, thanks a lot. If there are no further questions, I thank Daniel, and I will send you the YouTube link later. Yeah.
Okay, thank you very much. Yeah.
Bye-bye.
Bye.
Bye.